All right, let us summarize what we've learned in week 5. So first of all, we've learned what a second order linear differential equation is. We've learned how to set up an initial value problem. So remember that in order to set up an initial value problem, we need to specify the initial value of the unknown function and the initial value of the first derivative. And we have we have partially proved that an initial value problem has a unique solution. Specifically, we showed that this theorem is equivalent to a similar theorem for systems of first-order differential equations. The one thing that we didn't explain is the fact that this y of t has the same domain as p of t, q, g of t, and q of t, right? So that's what I didn't explain at all. Right? So the fact that this happens on the same interval, I didn't, explain it. We also applied this theorem to prove that the dimension of the space of solutions of a homogeneous differential equation is 2. So if we replace if the right hand side of our differential equation is 0, then we call such an equation homogeneous, right? So then the set of all solutions is a two-dimensional vector space. So the fact that it is a vector space is quite simple. So it's just you directly verify that a linear combination of solutions is again a solution, and the fact that the dimension is 2 is because of the existence and uniqueness theorem. And what we didn't learn now is just I wanted to tell you that a basis of the space of solutions is sometimes called a fundamental set of solutions. So you will see this. I'm not going to use this term in my lectures, but if you read textbooks or, I don't know, Wikipedia or whatever, then sometimes they call it the fundamental set of solutions instead of a basis. So the most general form of here is the most general form of a second order homogeneous linear differential equation. Right, so what it also tells us that if we found two linearly independent solutions, then every solution can be written as a linear combination of two linearly independent solutions. But in order to check if two solutions are linearly independent, we need to compute the Wronskian. And then because of Abel's formula, either the Wronskian is 0 everywhere, and then the solutions are linearly dependent. So this is only possible if the solutions are linearly dependent. Or the Wronskian is never 0, and then of course the solutions are linearly independent. But generally speaking, there is no, and not only we don't have a method to find solutions of a general second order linear differential equation, it doesn't exist. So here even linear differential equations, sometimes certain classes of differential equations with non-constant coefficients can be solved explicitly, but it is a rare thing. So usually if you have an arbitrary second order differential equations, you cannot solve it explicitly. Well, what you can do, if the coefficients of the differential equation happens to be constant, then it is possible to solve it explicitly. So by doing the following thing. So you need to set up the corresponding characteristic equation, which is just an algebraic quadratic equation with the unknown r. And if it has two real roots, then we are done. But if it has two constant roots or a repeated root, then we don't know how to deal with it yet. This is the topic of the next week.